Well, welcome back. Now we're going to be going over chapter 3, where we're going to be exploring number systems and codes. And it's actually helpful here. We've actually are showing these different ways of doing a representation of number: decimal, binary, octal, hexadecimal. The way that you see here is you have this 10, this 2, this 8, and a 16 is what it's referring to. And there's also this one other thing, this binary coded decimal. So these four binary digits represent one um, decimal digit. And so there's three decimal digits that are shown there. Okay, well, let's start to go through this. That should go fairly quickly. First of all, let's talk about the decimal systems. And so the radix or base of a number system determines the total number of different symbols or digits used by that system. The decimal system is a base of 10 with the digits 0 to 9 being used. And so thus, if we have four digits here, we are quite familiar with this. And so you can be thinking of 1962, how it would be laid out. Well, this is a similar thing that we can be looking at for other radixes that are different than 10. And so let's start to walk through that. The binary system has a base of 2, and the only allowable digits are 0 and 1. And so digital circuits use this a lot. It's either you have a 0 value or a 5 value of 0 volts or 5 volts. And so that's what we're trying to show here with a square wave, as this is called. This would be like a clock. But if it was binary data, it's not necessarily always going to be exactly even the way it's shown. So since a binary system uses only two digits, each position of a binary number can go through only two changes, and then a 1 is carried to the immediate left position. So all numbering systems start at 0, so keep that in mind. So this is a useful way to be comparing the different systems: decimal, binary, octal, and hexadecimal. So this would be binary over here, hexadecimal. This would be octal, and this would be decimal. So those are just gives you a comparison going from one to another if you haven't seen this. So this is what it looks like for binary. And so a lot of times, to make it easier, they group it by 4 bits. Those would be the hexadecimal way of processing 4 digits at a time. Each word is capable of storing data in the form of bits. A group of 8 bits is called a byte. And the least significant bit, or LSB, represents the smallest. And the most significant bit, the MSB, represents the largest value. So this would be the MSB and the LSB as we're looking at it there. The PLC memory is organized using bytes, single words, or double words. If the memory size is 1K, remember that's 2 times 10, 2 to the 10th, it can store 1024 words or 16,384. That's 1624 times 64 bits of information using a 16-bit word. You can convert from a decimal number to a binary number. And so this gives you the way of how you can do it, just doing it through division. And so this would be an algorithm. I'm not going to go through this in details, but another way to start to think about it is, over a period of time, you're going to become familiar with going from one to another by getting familiar with, say, like this hexadecimal number and what it would mean, or looking at these different things like this first bit here, you have a 0 and a 1, this would be 2. And so that would be something that you're seeing. So 2 and 8, and that's how you start to get the number 10, just to give you an idea. Negative numbers, binary numbers cannot use positive and negative symbols to represent the polarity of a number. In signed binary numbers, the leftmost bit is the equivalent of a plus or minus sign. 0 indicates that the number is positive, 1 indicates that it's number. And so this is one of many ways of doing it, but this is the convention that we're talking about here. Another comparison of expressing a negative number is to use the complement of a number. This is another way of using, trying to figure out how we're going to deal with negative numbers. The complement of a binary number, change all the 1s to 0s and all the 1s to zeros and zeros to ones. This is known as the ones complement. So that's fairly easy to see how that works. 2's complement is a number that, the binary number that represents when the ones are added to the one, when 1 is added to the 1's complement. 0 sign bit indicates a positive number, 1 sign bit indicates a negative number. So you can see there's various ways of encoding negative numbers. Octal means 3 digits, so that would be one of the ways. And so this is how we can be seeing a similarity. So you can see that we're using familiar digits, but it's only when you get to 8 where you can see that it changes, because there is no 8 or 9 in the octal system. It would be 1 0 and 1 1. So now with a radix, the first digit is 0, 8 to the 0, 8 to the 1, 8 to the 2. And so this is what we're starting to see laid out here. And so this is how we would do that conversion, and we have to come up with those values one radix digit at a time. Octal conversion to binary is fairly easy. And so this is how you just have to expand it out. And this is what we're showing here, that how that would work. The octal number 462 is converted to its binary equivalent by assembling the 3-bit groups. Hexadecimal, this is 4 binary digits, and this is where you have these funky looking things where you have, these are actually digits that you need, because in decimal we only have a possible of 10 different distinct type of ways of representing a number. So that's how that works. So once again, we have the same kind of convention, the radix, and so this would be 7 times 16 to the 0. The B, if we convert it to decimal, would be 11 times 16 to 1, and then 1 times 16 to 2. We calculate those and add them up, and that's how we get the actual value as a result. So converting decimal to hexadecimal, you just group bits, 4 bits. I've mentioned this already, and this is color coding is one way to make it easy for you to can see how that would go. And so we go to decimal. Now we're showing an example of how we go from hexadecimal to binary. Okay, binary coded decimal, this is another thing. So the binary coded decimal BCD system uses 4 bits to represent each decimal digit. The 4 bits used are the binary equivalent of the numbers of 0 to 9. So it's not as code efficient, memory efficient, but this is another way that you can be doing it. So this digit, you would just have it here. This would be plugged out in that set of 4 binary digits, and so forth for each one of these groups. So that's how we get binary coded decimal. To distinguish the BCD numbering system from binary system, a BC designation is placed to the right of the unit's digit. So decimal 4910 expressed in binary is shown like this. And so here we have a BCD 4910. You have put this little BCD down there. That's how you can, so subscripts are used to designate the base. That's a way of trying to make it so it's not ambiguous. A thumb wheel switch is an input device that makes use of the BCD numbering system. The input module attached to the thumb wheel has 1 connection for each bit's weighted value. Selected digit of decimal 8 outputs the equivalent of the bits of BCD data 1000 BCD. So that's how that works. So PLCs can contain number conversion functions, and so to convert to BCD instruction, we'll convert the binary bit pattern at the source address N7:23 into a BCD bit pattern of the same decimal value and stored in the destination address O:20. And so this is what we're seeing, the type of things that we can program. Now we're dealing with going from one format to another. So that at times can be quite useful. How to change format of data. Many PLCs allow you to change the format of the data that the data monitor displays. The change radix function found on the Allen Brady controller allows you to change the display formats of the data to binary, octal, decimal, or hexadecimal. When troubleshooting and trying to understand things that are going on, this can be a useful capability.